Hey guys, so I've been thinking, going back to the adventures I had at university with the students. We were supposed to be helping debug their projects. I've been thinking, and I want to do a bit of a different video today. So, considering what happened there, and um, I'm sure that all of my audience is going to understand everything in this video perfectly, and I'm not the best at explaining things, but I like to believe that I know a fair bit about at least what we're going to talk to about what we're going to talk about today. So um, we're going to talk about the basics of electronics measurements. So I'll try and show you how to measure voltage, current, and how to use an oscilloscope. Apologize if you see any weird blue flashes. There's a thunderstorm raging outside, and you might also hear the thunderclaps, or I forget the actual word for it. So um, let's bring out this thing, which is my trusty 87.5. This is one of the best electronics multimeters ever made. In my opinion, it's the best. Um, as I've told you, I'm very opinionated, and I love tools, and I love electronics and test equipment. So this one's pretty high up there. First of all, it's a fluke. But second of all, it's great because it explains one of the key concepts I want to explain. It makes very easy to understand one of the key concepts I want to clarify in this video, because this is one of the biggest things that I've seen engineers, brand new engineers, have enormous trouble figuring out. And that's the concept of measurement ranges. So as it stands, this multimeter has quite a broad dynamic range, if you could call it that. So it can go from basically 10 microvolts in the lowest reading. So the resolution is about 10 microvolts. And if you go into its highest range, you'll see that it's technically something over around 600, 700, 800 volts, something like that. I'm not entirely sure. It's technically a 60,000 count multimeter, but I'm pretty sure that you can read higher than 600 volts. It's maybe a kilovolt. I'm going to put it in, link it in here. So why do we need ranges on measurement instruments? Well, in order to have a versatile instrument, you would like to be able to measure, you can see microamps, and then below, behind the cable, because I keep them neat, there's a dedicated, no, sorry, it's here. It's a dedicated amp range. So we have milliamps, amps, and microamps. These are actually on two different circuit paths inside the multimeter. And we can see that it goes from 600 volts-ish, let's say, to 10 microvolts. So if you were to equivalent that to a single multimeter with one range covering the entire resolution, it would be massive. It would be something like, I don't know, over 8.5 digits. So 1,000 volts to 10 microvolts is, I think, 9 orders of magnitude, 10, almost 10 orders of magnitude. I'm sorry, I'm having some trouble with the math off the top of my head. So a kilovolt, a millivolt, and a microvolt would be 3 orders of magnitude. And we have 10 microvolts, so it's 8 orders of magnitude, basically. So it would be an 8.5 digit multimeter. So in order to measure the entire range that this thing could measure, you'd need a 3458A on one range, the 1000 volt range. But that's impractical because you can't squeeze a 28-bit analog to digital converter of the caliber required to get any useful readings in the the least significant digits in this size. Not yet. So what do? We try to get the best analog to digital converter we can get into here, the most stable one, the least drifty one, the one that consumes the lowest power in case of a handheld multimeter, right? And we try to make the most out of it. So how do we do that? Well, first of all, the reason and the horse I'm trying to beat even deader is you use ranges. So this being a 4.5 digit multimeter in its high resolution mode, doesn't need anywhere near close to 28 bits of resolution in its converter to read that. It actually needs, I'm gonna insert the number here because the math in my head at this point isn't really working. So you need far fewer bits. I think you only need something like 16 bits of resolution to get 40,000 counts. This is as thick as 60,000 counts, so it might have more. Let me just do some quick napkin math before I completely shoot off the rails here, and I'll be right back. Just a second. All right, so I remembered and I did some math. So 2 to the 16th. So basically, first of all, an A to D converter, which has 16 bits, can have a maximum value of 65,536, right? So this being a 60,000 count multimeter, it's probably got a 16-bit ADC inside. It probably has a bit more than that in order to do some linearization and correction and stuff like that, but let's assume it to be a 16-bit ADC, right? So the highest value it could generate, it could convert, would translate into 65,536. You need to squeeze the input voltage or current or whatever you're trying to measure into that interval. So the first way to do a range is to divide the input voltage. So in case of the higher voltage ranges, like the 1000 volt range, you wouldn't like to connect the entire input voltage to the ADC because that would be very bad. 1000 volts through something like this in your hand is only safe if you have some protection. So you divide that input voltage with a known resistive divider, and then you buffer the output of the resistive divider so you don't load it down and you don't cause errors in the reading. And after you do that, you make sure that the input is divided so as to fill the range of the ADC. So let's assume that the ADC's maximum range is, I don't know, 10 volts. If you want to fill 10 volts with a 1000 volt input, you need to divide that by 100. The other way you use ranges in the lower, basically in the lower range, is to amplify. So for millivolts, if we have 600 millivolts max scale, or let's say 100 millivolts max scale, and the input is 10 volts, well, you need a gain of 100 to fill that ADC range. So that's basically how you set the ranges in a multimeter. And this is why you do it. You want to fit as broad as a measurement interval in as small of a package as you can. Now, when you need to read 10 volts down to the nearest 10 nanovolts, then you'd need a much more complex instrument, like the aforementioned 3458A. The problem with going higher and higher in resolution is that the usefulness of the information you get out of those analog to digital converters is increasingly more meaningless. So the readings in the least significant bits become more and more useless. and you can trust them less and less. Alright, so this is about ranges. I'm going to show you exactly how we set up a measurement for voltage and for current, and I'm going to try and explain why a multimeter is fully differential, always. I'll be right back. Alright, so I've connected the probes of the multimeter in the following configuration. So common goes to the black lead always, and the positive lead or the red lead is connected to the volts, ohms, or diode, temperature, etc. Plug basically. And I have this connected to my like telling you this would be an admission of guilt. So I got another source meter. I might show it to you a bit later. It's a 2-3 it's a 237. So a 237 is a 236 with an extra kilovolt range on it. That's all. It's a high voltage source meter unit. Anyway, so why I'm using that is that it's very easy to generate both voltages and currents, and I don't need to worry about blowing fuses in this because of a bonehead mistake or something like that. So I'm going to set it up to let's start at 4 volts, and you can see that at 4 volts we're pretty much bang on. Like, this thing is really close, and you can see that the high res button didn't do anything. Why didn't it do anything? Well, high res is basically it's adding another digit, but only if you're within specific ranges. So let me try and convince it to go to more digits. So you can see we get 4.5 digits, but the scale now, the range is now only 2 volts. If I go higher, it will switch back to 3.5 digits. Actually, it's 3 3/4. I'm not even sure. Anyway, let's see just how high it goes. So it goes 8, 9, 10. Okay, so it's still 4.5 digits, but up to 20 volts. So if we go to 21 volts, it's gone. If you go to 19, what? Yeah, so 19 is 18.005. So we can see a millivolt and 20 volts, which is pretty good. And you can already see that my source meter, the brand new one, is a bit out. So I trust this more than that. And I've actually double checked this with the 6.5 digit meter that I have. And the source meter is the one that's out. So how do you connect a voltmeter, basically? So a voltmeter is characterized by having, ideally, infinite input impedance. So infinite input impedance, it means that if you connect the probes to any point of a circuit, there will be no current flowing into the multimeter probes. Basically something like the inputs of an op-amp. That's not entirely true, but these things usually have very high input impedance. These meters usually have impedances of, like, resistance. Basically it's seen as a resistance of 10 megohms or greater in a circuit. Now if I go to my source meter, and I'm going to try and take a photo of this and insert it here. If I go to set it to 1 volt, and then I go to the smallest measuring range that will lead me with an answer, the current the multimeter is drawing is around 0.1 microamps. So a volt and 0.1 microamps is about, if I'm not mistaken, around 10 megohms. Let me double check that and I'll tell you if I'm right or wrong. Yeah, so I don't know what's wrong with me today. It must be a bit rusty. So if you divide 1 volt by 10 to the minus 7, which is 0.1 of a microamp, you get 10 million. So this thing has a pretty darn close resistance, input impedance to 10 meg, right? Okay, so why would you care about input impedance? So every time you measure voltage, you're drawing a bit of current in order to satisfy the either the voltage divider or the bias current for the operation for the amplifier, which is for the lower ranges or stuff like that. So all those things are not ideal, and they need a bit of current in order to work, basically, to bias themselves to whatever. So if you're not cognizant of what you're measuring, your measurement might load a sensitive circuit down below its operating point. For example, and this is one of the easiest things to demonstrate, but I don't have anything of the sorts at hand. So if you have like a Geiger counter, a Geiger tube power supply, usually they're meant to run at very low currents, below 100 microamps usually. And so the power supply is not capable of delivering much power, much current, right? High voltage, but its equivalent series resistance is very high. So the voltage sags profoundly under any slightest load. If you come along with 10 megohms of input impedance, you're going to load that power supply enough so that the reading you're going to see is not anymore the reading of an unloaded circuit. Okay, that's a bit of a tangent, but anyway, multimeters have non-ideal behaviors, as every other piece of equipment you would have. One of the other disadvantages of a multimeter is that you're using quite a weird, like it's not a very sophisticated means of probing, and you can pick up quite a lot of noise on the measurement. So you have to be aware of that as well. These things, by being floating and being usually used to measure quite large voltages or significant currents, are not usually that subjected to noise, especially to mains noise. But it can affect them as well as every other circuit in the world. Okay, so this is how you measure voltage. You're aware of the fact that you want to put the probes of the multimeter in parallel with the points on the circuit you want to measure the voltage across. You don't put anything else into the circuit, right? And you hope for the best. So you hope that the node you're trying to measure is not too sensitive, or you hope that your meter is good enough so as not to load the circuit down. That's usually not a problem for most things, but usually high impedance circuits and high voltage circuits are commonly subjected to this issue. Okay, so red probe, and the voltage range common is in the ground, always stays here. I'll never move this, and that's how you measure voltage. How do you measure current? Well, give me just a second and I'll show you right away. All right, so what we have here is a connection for measuring low currents. So we're in the microamp range. The source meter is turned off, and you can already see that there's a bit of a problem. We're reading 0.3 of a microamp. Now, I'm not entirely sure whether it's noise or it's just 0.3 of a microamp somewhere. You can pretty much tell once we turn on the source meter and make it sort some current through the circuit. So I'm gonna hit operate. I'm sorry, I'm in AC. I forgot. Flukes, weirdly, this is an electronics multimeter. First, it defaults to AC microamps. Why? Anyway, okay. So we can see that I've the multimeter is now connected to a different terminal. So how is it doing it? Well, it's still only a glorified voltmeter, so it only measures a voltage. So what is it doing with this voltage? Well, it's applying it to a resistor, and it's basically measuring the voltage drop across that resistor, and it's doing Ohm's law better than I am to measure current. Basically, that's how this sort of multimeter measures current. Now, there's a problem with that, which is that in order to be able to measure that current, you need to insert a resistance of a significant value so as to generate a significant voltage drop, which the ADC can measure. And that voltage drop is usually referred to as the burden voltage of a multimeter when it's used to as a current measuring device, sparking the whole Dave Jones EV blog microcurrent thing. I actually have one of those somewhere around, but it's been discussed so many times that it's yet again, I'm beating the same dead horse. So when you're trying to measure current, you are going to put the leads that you want to measure the current through in series with the thing you're trying to measure the current for, basically. This is different from the voltmeter approach due to the fact that an ideal current meter has zero resistance, right? This is not ideal. It has some resistance. It needs to drop some voltage in order to sense that current that's going through it, but it's pretty close. I'm actually thinking that it's so far off because the voltage that I'm dropping across that shunt resistor inside is so large that it's bordering on the compliance voltage set on the source meter. Give me just a second, I'll see if I can figure this out, because it's beeping kind of red. It's blinking red lights at me, and I'm pretty sure it's almost maxing out the scale or on the source meter or something like that. Right, so I was right. It's still a bit off, but nowhere near 7 microamps off. So you can see it's now 99-ish microamps. It's pretty good. What was happening was that the source meter was behaving as a close to ideal current source. So a current source, first of all, has infinite output impedance, and it has an infinite compliance voltage, which means that you can have you can force the constant current through any load you'd ever want, right? So either I put a micro ohm here or a giga ohm, it would force the same 100 microamps through the circuit. Now, forcing 100 microamps through a micro ohm is very easy, right? But if you want to do that to 10 gigohms, then you're dealing with some very, very high voltages. So that's kind of hard to do. So the compliance voltage for this range, it's now around, it's set to 1 volt, but it's only at 10 millivolts. So in order to measure that 100 microamps, the multimeter is losing 10 millivolts, is giving away 10 millivolts to its own ADC inside, and you're robbing the circuit of those 10 millivolts. That's one thing to be very wary of when measuring currents with a multimeter like this and a circuit. Okay, so this is how you measure voltage or current with a multimeter, why you use ranges in order to expand basically the dynamic range of an instrument. It's not the dynamic range, it's more like the usefulness of an instrument, but using the same number of AD converter bits. What else could I show you? You can measure resistances with this thing as well. So how you measure resistance is basically the exact opposite of how you measure a small current. The multimeter will generate a very small current of around 100 microamps or so and push it through the leads to the resistance you're trying to measure, and then it will measure the voltage drop. And by doing Ohm's law again, it will be able to tell you the resistance value. I'm not going to show you how to measure a resistance because I'm going to open up a whole can of worms about 2-wire and 4-wire and other stuff like that. Okay, one last thing I wanted to mention. So, by definition, a multimeter, regardless of its make, model, complexity, anything, is a fully differential instrument, which means that it will only measure the voltage between the two probes, right? What does that even mean now? Well, if I put this probe into the source output of the source meter, you'll see that there's no reading on it, and there's a volt here with respect to this terminal. Okay, why am I not seeing that volt? If I touch this thing to ground, will I see that volt? Well, let's see. Yep. And why is that? By the way, I'm touching it to the ground terminal and the power supply I have here, and trust me. Well, why is that happening? It's still fully differential, but now we have introduced a new variable to the discussion, which is we have established a ground. So if I connect this black probe of the multimeter to any point in the circuit or wherever, if I stick it into the earth, basically, I shall have defined a ground. Any voltage this multimeter will measure from then on will be with respect to this probe and only this probe. Okay, this is a very stupid conflict I had with somebody at some point. I'm not going to name names or anything, but what they were asking was, I have two 3458As. I want to measure a shunt in a circuit. And instead of just going like it was a high side current sensor or something like that, I don't know. And instead of going like I'm measuring straight across that thing, it's fully differential. It's reading only the voltage drop across that goddamn shunt, right? Which you can see that, so this multimeter is very non-conductive. Oh, say hi to Pesto. Pesto is always impressed by the fluke. So instead of putting two probes over that current shunt and measuring the voltage drop on that current shunt, which means measuring the current through that side of the circuit, I was thinking, what if I connect both negative leads of my two multimeters, and then I put one red lead before the resistor and one red lead after the resistor, and I subtract the readings from them. And the obvious reason is that, well, no, because every multimeter is a differential input, as long as, for these it's indefinite. For a bench multimeter, any input can be 1,000 volts over earth, basically, something like that. So it doesn't matter. If you're measuring with this thing can be floating at 50, 60,000 volts, and you could be measuring 3 volts on something, no problem. But if you have a mains referenced multimeter, which means that it's not the input which is mains referenced, that never happens. Only the case of the instrument is referenced to mains, which means that if you exceed a specific voltage on one of the inputs, that voltage may cause breakdown and discharge inside the device, which will lead to it being damaged. All multimeters are differential. All of them. They just measure the potential difference between these two probes, these 2 points, actually between the common and the voltage input on the multimeter, right? So I hope that's clear enough. You don't need two multimeters to measure differentially unless, gosh, I don't even know why. Like, if you need more voltage, you're only doing one thing, and that is using two non-synchronized analog to digital converters to sample a voltage with respect to Earth at different points in time, which means that if you're measuring something in 2 points with respect to Earth and you're not doing it at the same time, you're going to measure anything but what you're trying to measure. You're going to measure noise. You're going to measure anything but what you want to measure. All right. So, what have we learned today? I don't even know, man. I hope you just understood what to do with like a multimeter. Oh, by the way, don't do this. See, it even beeps at you and tells you you've got the lead in the wrong place. Don't do that and then stick it in the power socket, in the plug socket, because you're gonna break it and you might break yourself. So always be cognizant of what you're trying to measure. Also, don't measure things like this. These guards here are there for a reason. They're for you to have some purchase and be able to dig through an oxide layer, but not have your fingers slip on the thing you're trying to measure. Be wary of these things, because you can measure up to 1,000 volts with these things. Like, I have done that. And 1,000 volts, if it's got any amount of kick behind it, even that source meter I was talking to you about, you're dead. That's it. Even 380, 400 volts, three phase, if you're going to measure that, you're screwed. Okay, I promised I would show you the 237. Be right back. Alright, so sorry about the weird light shading and stuff like that. So, a quick backstory. So, ever since somebody on YouTube, I'm not going to tell who that is for the 1,000th time, somebody on YouTube showed a video about these particular things. They've been kind of an object of desire for me, and I don't know why, because they're pretty weird. Like, they're very interesting devices, and they're very useful, and they used to cost inordinate amounts of money, like in excess of $10,000 for one of these things back in the day. They have extremely good input impedance, characteristics. They can measure currents almost as well as my electrometer, which is no small feat. But why do I need two of them? Well, of course I don't, right? So initially in the series, so these are before the time of the 2000 series, the small shoebox half unit things you know from Keithley today. This is the 230 series, basically. There's three models in the series. There's the 236, which is the baby, the basic model. There's a 237, which is this, but with an extended high voltage range, which is up to 1,000 volts. So you can see this would be the 1.1 volt range, 10 volt and 100 volts. And if you go to 110 volts actually, and if you go to even more than that, I'm not sure why it's not letting me do what I'm trying to do. Oh, it's 1100 volts. Sorry, I didn't see the decimal point. So you can have up to 1100 volts at 10 milliamps. And there's a third model, which I'm hoping to never find at a reasonable price on eBay, because I might get it, which is the 238, which is the same thing as this one, but it can output 1 amp at less than 15 volts. So they're basically the same device with just some minor differences between them. And as I've shown you in the source meter overload video, which had a very clickbaity and deceptive title, these things were used in semiconductor characterization. You could basically measure material constant parameters, stuff like that. I discussed a bit about what you could do with these things in the previous video, but the extended ranges of the 237 and 238 had some benefits. For example, they don't have really any pulse capability for short high power pulses, but you could go into stuff like higher power devices, like with the 1 amp version. You could go into higher power diodes and characterize them more fully. And with this 237, you could characterize the breakdown voltage of, for example, diodes and transistors and stuff like that. And you can study their leakage at higher voltage, and you could study their characteristics basically. And they all had various advantages. Needless to say, this one was the cheapest of the three of them, but I actually got this one for cheaper than I got this one. So there's still a seller on eBay. I'm not gonna tell you their name because they're not paying me, but there's still a seller on eBay who has around a few of these. So the one I bought the 236 from had 20 or something, 20 something, 26 of these, and this guy had like 19 237s. And don't go paying the eBay's Calper price of over $1,000 or $2,000 for one of these. They're not worth it. Don't get me wrong, they're insanely cool, and just the fact that you can read Keithley here for me is like an absolute wonderful thing, but they're not worth it. This one might be worth it if you can get a very good recapped model with good capacitors inside and freshly calibrated and stuff like that, because it will be the cheapest power supply that goes up to 1,000 volts that you could get. Oh, and it goes negative as well. So yeah, you find me a positive and negative 1100 volts power supply for less than 500 bucks. I double dare you. All right, so oh, and the 238, for me that one is the hardest, the most bitter pill to swallow, because having a 1 amp capability isn't really that useful. Like, you can extract enough information about a diode running at 100 milliamps rather than running at 1 amp. That's more for my understanding would be for Kelvin resistance measurement for low resistances or something like that, or material parameters like, I don't know, the number of ohms per square of like a silicon wafer or something like that. I have no idea. Or damn. Anyway, so now you know that I have two Keithley source meters, and I definitely don't have a problem, and I definitely don't do far too much eBay shopping. Oh, by the way, I'll insert a picture of the VF and the breakdown voltage of 1N40, 148 if I can find it, and I'll try and squeeze in a Nixie tube being lit up, like oh hell, why not, let's do it. So I have some of these things. They are, I don't know what, IV something, IN4, okay, and these are very nice Nixie tubes, and we're going to try and light one up. I'm not sure how well this is going to go. We're gonna start, we're gonna say 100 microamps is fine for compliance current, and we're going to hit enter, and then so go to a more like reasonable digit. Sorry, that's still fine. Okay, and I want to go, oops, Jesus, sorry, professionalism like you've never seen before. Pesto is currently trying to gnaw on the triax. Alright, so we can see we have either the letter 9 or the letter 6. Number 9 or 6. Jesus Christ. I need a holiday. Anyway, it's actually still not as bright as it would like to be. These gases, the Nixie tubes have a very weird characteristic. So once the discharge inside ignites, its resistance drops abruptly. So you need to aggressively limit the current. That's why you can't just slap 170 volts on these. That's the ignition voltage. But you also need to limit the current through these things in order to not, well, basically destroy them. So yeah, this is what a Nixie tube looks like when lit up by a former $20-something thousand source measure unit. I hope you have enjoyed this, and I'm trying not to electrocute myself. I'm just going to turn that off to be safe. And I'm going to set it back to something more reasonable, so even if I turn it to operate, it won't kill me. By the way, funny thing, this is the same LED. The only difference between the two front panels is that the operate here text is a bit larger, and it has this nice lightning bolt there. This is, yet again, the cheapest 1000 volt positive or negative power supply you could actually get on the market, and it can do up to 10 milliamps at that voltage, which is, geez, not bad, right? Okay, so I'm going to have to cut it closed here. I was going to talk to you about the test fixture that I found for the, oops, sorry, you're gonna get all motion sicknessy. So what I meant to say was that I wanted to talk to you about the just a second. What I meant to say was I actually got this thing in the meantime. It's the test fixture for the 4145. I'm sorry for the sickness inducing footage you're seeing right now. It came with the suitcase and all the plugins and stuff like that, and the cables are underneath here, and it works very nicely. And yeah, I was going to talk about that too, but it's already like 45 minutes into this video, and yeah, no more ramblings about my university years, and yeah. Thank you for watching, and keep an eye out for these things. You can usually find them on eBay, I hope, still. But don't get into gear acquisition syndroming like me. Have a great weekend, and thank you for watching. Bye, guys.